Hey guys, so this is section 8.1 where we're talking about the relative stability of the solid, liquid, and gas phases. So first of all, for something to be stable, the criteria for stability is that the free energy has to be minimized. And just remember that the chemical potential is equal to the partial of the free energy with respect to the number of moles at constant temperature and pressure, but we can write G as the molar Gibbs energy times the number of moles. But then we see here, this partial just ends up being the molar Gibbs energy. So just a reminder that the chemical potential is equal to the molar Gibbs energy for a single substance. So if we take the differential of both sides of this guy, we showed in section 6.2 that dG is equal to negative S dt plus VdP. Which means, okay, so now we're looking at this and this. Take the derivative with, we divide by the by dt, make it a partial. We get partial u, partial t at constant p is equal to, keeping p constant. This term goes to 0, and this is just negative molar entropy. Doing the same thing, okay, taking the partial of chemical potential with respect to pressure at constant temperature. This term goes to 0. We get just the molar volume. Okay, so we'll show why that's nice right now. So we know that the molar entropy or entropy is always a positive number, which means that looking at this equation right here, because the entropy is always positive, that means that the partial of mu with respect to temperature at constant pressure has to be always negative, which means if the temperature is increasing, that means that the chemical potential is decreasing. Likewise, the partial of mu with respect to P at constant T, the volume has to be a positive number, which means this partial has to be positive, which means if the pressure is increasing, so is the chemical potential, and vice versa. The pressure is decreasing, the chemical potential is decreasing. Over here, if the temperature is decreasing, then the chemical potential has to be increasing. So we know that during a solid to liquid or a liquid to gas phase transition, we have to put enthalpy in. Delta H is always positive, right? You have to put thermal energy in to that ice cube to melt it. You have to put thermal energy into that water to boil it. Because during a phase transition, the system is always at equilibrium, delta G is equal to 0, but delta G is delta H minus T delta S, meaning, we can rearrange this and see that delta S during a phase transition is equal to delta H over T. Because delta H for a phase transition, always going, from solid to liquid or liquid to gas, is always positive and temperature is always positive, that means that delta S is always positive. Which means that when we go from the solid to a liquid phase, the entropy of the liquid is greater than the entropy of the solid. Likewise, going from the liquid to the gas phase, the entropy of the gas is greater than the entropy of the liquid. Period. We don't have to go look at available states or anything like that. We see it directly from this equation right here. Now, looking at this graph right here, the chemical potential versus temperature, where each of these lines is the chemical potential for the solid, liquid, and gas phase at the different colors. These aren't actually linear lines. They're pretty close. In reality, they're slightly logarithmic, but it doesn't matter for our purposes here. And from this equation, we see that the molar entropy is the negative of the slope of each of these lines. So remember that the criteria for stability is that the chemical potential, the molar Gibbs energy, is a minimum, which means that if we look at this line for the liquid here and the solid here, at any temperature beneath this temperature right here, the solid has a lower chemical potential than the liquid, and that means that the solid is a stable phase. Likewise, over here, the liquid is at any temperature in here, the chemical potential for the liquid is lower than that for the solid and for the gas, and that means the liquid is the most stable phase. Once we get over here, the chemical potential for the gas is lower than that of the liquid or the solid, and the gas is the stable phase. where these lines intersect, that's the transition point. So where the chemical potential for the solid and the liquid are equal, right here at this temperature, that temperature is the melting point of that substance. Likewise, where the chemical potential for the liquid and that of the gas intersect, that temperature is the boiling point. Now, it's possible to take a liquid, and if you cool it down really fast, you can get a supercooled liquid. In other words, you get a liquid at temperatures down here, but it's only metastable. It's not stable. You disturb the system and it crystallizes. Likewise, you can get a superheated liquid, a liquid whose temperature is higher than the boiling point, also metastable. Kind of dangerous too, because as soon as that is messed with, then what happens is it goes from liquid to a gas really fast, and that can be dangerous. Notice that because the entropy of a liquid is greater than the entropy of a solid, the slope of the line for the chemical potential versus the temperature of the liquid is greater than that of the solid. Likewise, because the entropy of a gas is greater than that of a liquid, the slope of this line is greater than the slope of this line, more negative. Now we're going to look at what happens when we change the pressure. So we're looking at this equation over here, how the chemical potential changes with pressure at constant temperature. It's equal to the molar volume. We know it's always true. The molar volume of gas is a lot bigger than the molar volume of liquid. Most of the time, the molar volume of liquid is greater than the molar volume of a solid. One notable exception is water. Right at its freezing point, liquid water is actually more dense than the solid ice. And so it's the volume of the liquid right at the freezing point to just above it. It's smaller than the molar volume of the solid. So, in these two graphs right here, the one on the left shows what happens if the molar volume of the liquid is greater than the molar volume of solid, so not water. On this one, it's showing what happens if the molar volume of the liquid is less than the molar volume of the solid, so something like water. What these are showing is the effect of pressure. So in these graphs, the solid line is at pressure 1. The dashed lines, a little harder to see, are at pressure 2. And pressure 2 is greater than pressure 1. So also down here at these temperatures, the temperature without the mark is the temperature at pressure 1. The temperature with the mark is the temperature at pressure 2. So what we see, looking over here where the volume of the liquid, the molar volume of the liquid is greater than that of the solid, what happens when we increase the pressure from P1 to P2, because the molar volume of the liquid is greater than the molar volume of the solid, the slope of the line, or rather how the chemical potential changes with the pressure, is greater, okay, for the liquid than the solid. So we can see the difference, it's kind of close here, between the green dashed line and the solid green line is smaller than the difference between the solid blue line and the dashed blue line, because there's the chemical potential changes more with pressure for the liquid than the solid. Over here, it's the opposite, right? Because here, this is the case where the molar volume of the liquid is less than that of the solid, and so that means that the chemical potential changes less with pressure for the liquid than it does with the solid, and so the difference between the solid and the dashed lines for the liquid here is smaller than that of the solid and the dashed lines for the green one for the solid. On both of these situations, the difference between the solid and the dashed line for the gas is a lot greater than either the liquid or the solid. So let's look what happens at the melting point here. So in this case, where the molar volume of the liquid is greater than that of the solid, and what happens when we increase the pressure, this line goes up here, the chemical potential goes up, and where it intersects the green dashed line, which is right about there, that temperature is higher than the temperature at the lower pressure, and so we have freezing point elevation. Likewise, same thing for boiling point. As we increase the pressure, the dashed line goes up, And where it intersects the blue line is at a higher temperature than before we raise the pressure, so the boiling point goes up, boiling point elevation. Now over here, as in water, where the molar volume of the liquid is less than that of the solid, because the green dashed line, the chemical potential for the higher pressure goes up more than it does for the blue dashed line, the liquid, where the blue dashed line and the green dashed line intersect right there is at a lower temperature. So you see we have freezing point depression in this case as we increase the pressure. But we still have boiling point elevation. Triple point and sublimation. So for carbon dioxide, for example, not the only substance like this, chemical potential versus temperature. At this pressure right here, the chemical potential for the liquid is always higher, the blue line right here, than that of the solid or the gas. And so that means that the liquid is never the stable state. It's never the energetically favorable phase for the substance to be in. At this pressure right here, it'll go, as you increase the temperature, from a solid directly to a gas. It'll sublime. That's sublimation, dry ice. However, this graph on the right-hand side is at a higher pressure, and it ends up at this pressure. There is one point at which the chemical potential of the solid, the liquid, and the gas is all equal. That temperature is called the triple point. At that temperature and that pressure, what happens is it's really cool. You have all three phases coexisting in equilibrium. If you've ever seen it, it looks really cool. You have vapor, you have liquid, and solid all coexisting in equilibrium. That's called the triple point.